Good afternoon, dear friends. We begin the third lecture of the topic Distributed Elements Circuit. In this lecture, we are going to obtain the basic equations of lines with distributed parameters. These equations will allow us to study and, I hope, understand the electrical processes in such lines. Today we will briefly recall what we talked about in the previous lecture, get the basic equations of the line and analyze them. So let's begin. In the previous lecture we defined the main feature of lines with distributed parameters. All currents and voltages in such lines are functions of two variables, time t and spatial coordinate x. As a result, the currents and voltages in the line can be found as a solution of differential equations or system of such equations in partial derivatives. This greatly complicates the analysis of processes in lines with distributed parameters. Lines with distributed parameters are characterized by four primary parameters. They are determined by the physical characteristics of the material from which the line is made, as well as its construction. In this lecture, we will use these parameters to construct equations describing the relationship between currents and voltages in lines with distributed parameters. First of all, let's remember what we talked about earlier. In the first lecture of our YouTube channel Electrical Engineering Theory, we talked about the fact that there are two letters designations for electrical voltage. According to Wikipedia, we can use either the letter V or the letter U for this. Given the fact that in some electrical disciplines the letter V is used for voltage losses, we have always used and will use only the letter U for denote electrical voltage. Moreover, to denote a voltage that does not change over time, we will use the capital letter U. And to denote voltage that varies with time, we use the lowercase u or the u of t to emphasize time depends. Well, now let's finally start creating basic equations for lines with distributed parameters. To construct the basic equations, we can only use the theory of lumped circuits, just because we don't know anything other than that. Therefore, we consider a section of a line with distributed parameters which has an infinitesimal length. Let's say that this section is located at a distance x from the beginning of the line. As you remember, in the previous lecture we talked about the fact that a section of a unit length of a line is characterized by primary parameters: linear resistance, inductance, capacitance, and conductivity. You can watch this lecture on our YouTube channel at this link. A section of infinitely small length can be considered as an electrical circuit with lumped parameters. These parameters are equal to the product of the corresponding specific parameters and the length of the section. This length is dx. For this section, you can compose equations according to Kirchhoff's laws. To draw up equations, consider the currents and voltages that take place in this section. Let current I and voltage U acts at the beginning of the section. This current and this voltage change along the length of the line at a rate defined as di by dx and du by dx. When passing through a section of length dx, the current will change by the value defined as particular derivative di by dx multiply dx, and the voltage by the value du by dx particular derivative multiply dx. Then, at the end of the section, a current is the sum of previous value and the value of this change. Similarly, the voltage at the end of the section can be defined as the sum of voltage at the beginning of the section and the value of its change, the value du by dx multiply dx. Under the influence of voltage at the end of the section must be a current in parallel connected elements G0 and C0, which we designated as I0. So now is everything ready to write our equations. So let me get the first equation of the line. To do this, we will write an equation according to second Kirchhoff law, also known as the law of voltages, for a circuit that is formed by a voltage at the beginning of the section, a resistor R0 dx and coil L0 dx, and a voltage at the end of the section. Go around the circuit clockwise. The voltage at the beginning of the section is directed against the circuit bypass, so it enters the equation with a negative sign. The current I coincides with the bypass direction of the loop, so the voltages at R0 dx and L0 dx enter the equation with a plus sign. Minus u and plus u, there and there, and up to 0. Reducing the remaining terms of the equation by dx, we obtain the first equation for a line with distributed parameters. This equation relates the rate of change of voltage along the spatial coordinate with the current and that acts in the line and with its time derivative. Notice that the minus sign in front of rate of change along the spatial coordinate. We will talk about the nature of this sign later. For now, just we remember this equation and move on to getting the next equation. To obtain the second equation of the line, we composed the equation of the first Kirchhoff law, known as the law of currents, for this node. Current I enters the node, so there is a plus sign in the equation. The current I0 and the section output current both exit the node. Therefore, in the equation, they are taken into account with a minus sign. In turn, the current I0 can be found as the conduction current G0 dx plus the capacitance current C0 dx. We find the conduction current as the product of the value of this conductivity and the output voltage of the section. And capacitance current is the capacitance value which is multiplied by the derivative of the output voltage with respect to time. Substituting the current I0 into the original equation, this equation, after some transformation, we can obtain the second equation of the line. This equation relates the rate of change of current along the spatial coordinate with the voltage in the line and the derivative of this voltage with respect to time. Let's analyze the equations we got. As you can see, telegraph equations are a system of equations that simultaneously described the law of change of both current and voltage in time and in space. The first equation of the system is actually an equation of Kirchhoff's second law. Each term of this equation is measured in volts divided by meter. The second equation is Kirchhoff's first law equation, and each term is measured in amperes divided by meter. Thus, we came to the fact that currents and voltages in a line with distributed parameters obey Kirchhoff's laws. We can assume that, in general, all circuits with elements with distributed parameters will also obey Kirchhoff's laws. Thus, Kirchhoff's laws are universal laws that apply to all electrical circuits without exception. Let's pay attention to the fact that the derivatives du by dx and dEI by dx in both equations are preceded by a minus sign. All the textbooks say that this means that the voltage and currents in the line decrease with distance. In general, this is true and corresponds to our intuitive ideas. Indeed, in the conductors of the line, due to losses, currents and voltages will disappear. But let's take a closer look at the equation. The partial derivatives with respect to the x-coordinate will be negative if the right-hand side of the equation is positive. Consider, for example, the first equation of the system. The product of R0 by the current is positive because the current in the line is directed in the direction of the increase in the x-coordinate. But the component L0 multiply di by dt can be negative if the current decreases with time. In this case, if the modulus of the product R0 by the current is less than the product of the inductance by this derivative, then the right-hand side will be negative and the voltage in the line will increase with increasing distance from the beginning of the line. Such a phenomenon is still difficult to explain physically. But in our later lectures, we will, when we will study wave processes in lines, we will learn why this can happen. This is the first, but not the last, oddity that we encounter when studying lines with distributed parameters. And about conclusions of this lecture. Firstly, we can see that to create equations of a line with distributed parameters, we must use the theory of circles with lumped concentrated parameters, simply because we have nothing else to use. For this, an infinitesimal section of the line is considered, for which the distribution of parameters can be neglected. For this section, with the help of Kirchhoff's first and Kirchhoff's second laws, we can obtain telegraph equations that relate the partial derivatives of currents and voltages to the primary parameters of our line. The telegraph equations are also reflections of Kirchhoff's laws, so we can assume that Kirchhoff's laws are general laws for all electrical circuits. But telegraph equations are difference equations with partial derivatives. Their solution is possible only in some special cases. The solution of telegraph equations in one of these cases, when currents and voltages in lines change according to a sinusoidal law, will be the topic of our next lecture.